the next little subsection, I want to talk about resizable arrays, a simple trick to get arrays that can, to the outside world, appear to change the size. Under the hood, they don't. It's an amortization trick, how you can create new space when you need it. I suppose many of you have seen this, so I'll go over this a bit more quickly. One little comment is you can see an array as an abstract data type where the operations are create me one of size n, and I can get and set certain cells at the index I. So of course, most programming languages have special syntax for specifying this because you use arrays all the time. But that's the usual way how arrays work. Now, I would still say an array is usually not seen as an abstract data type, but rather as a fixed specific data structure, because I don't know of a programming language that uses arrays for anything other than a contiguous piece of memory. But maybe it's sometimes useful to think about these operations specifically. That is what makes an array, really. Now, how can we do a stack of unbounded size with arrays of fixed size? We have to somehow allocate new arrays, obviously. And we can do this as follows. This was the invariance for maintaining a stack in an array. We have an array S, and it was drawn like this, right? You remember just a couple of slides back. And it had a certain capacity C. And we had a pointer to where is the stack currently. So point top would essentially store the index of the topmost used element. Now the new thing is that we insist that at any point in time, this capacity is sandwiching the number of elements in this way. N must be at most the capacity. Well, we have to store the elements. And we also want that the capacity is not 4 times bigger than n. So we don't want an overly large array if there's not also many elements. If we can maintain this invariant at any point in time, it means we can always add more elements because the capacity grows with the number of elements. But what I haven't told you so far is how we can maintain this invariant. And a conventional easy way to do it is as follows. Before we push a new element, we check if we've reached the current capacity. And if so, we allocate a new array of twice the size of the current size, and we copy over all elements. So that was the current capacity C. Now we double it, and we make sure that this lower part is copied over from here. That's quite expensive, but we'll see that it pays off in that whenever we have this expensive operations, there's many cheap operations after that. The same thing if we remove an element and that brings us below our capacity bound. We do the very same thing, interestingly. We allocate a new array of twice the size of the current stack and copy all elements. And that's it. It's simple to implement and program, but I want to make sure that you understand what this is about. So let's do this little question. Which of the following statements is true about a resizable array when it currently stores n elements? And again, read very, very carefully. There's nitpicks in the formulation. What I mean by nitpicks is pick the statements that are always true. Not those that sound just reasonable, but those that are really clearly true. In a sense, this question is my way to see, have they seen resizing arrays? Yes, but have they seen it and totally internalized it? That's what this question gets at. And from a theoretical perspective, if you like. Okay, I think most people have voted. So let's see what you came up with. And I'll show you my answer. And want to briefly tell you a little bit about why I think the others are not as true as I would like them for this question. Oops, that was not what I wanted. Um, um, okay, I didn't want to reveal the answer right here before we do the analysis, but because most people have seen this, maybe I'll do this anyway. I think this is the correct statement, and I'll justify the statement for you in a minute. The first statement is not really true because the number of elements that are currently stored that might fluctuate up and down, and it's not always exactly 2n. Nitpick, as I said. Adding and deleting an element at the end takes constant time. So here the nitpick is, if I say constant time, this means worst case constant time. If there's no other qualifier, you have to assume it's worst case. And that's not true, because in a resizable array, if we have to resize, it's expensive, takes linear time, as we'll discuss. And the last point is, inserting and deleting any element takes order 1 amortized time. If this was combined with the second answer, it would be true. The last element can be deleted in amortized constant time. I cannot take out any element in the entire array. I would have to shift the rest over. Okay, that was maybe a bit of a mean question, but I wanted to see if you can follow along with this. But let's briefly do this amortized analysis of the resizing arrays, because amortized analysis will come up later in the class in a more complicated setting. So it's useful to get this sorted once and for all here in this simple setup that is probably familiar to you guys. Okay, what is amortized analysis about? It's a common term in algorithms and data structures, so definitely you should be able to recognize what it means. It's the concept that any individual operation, in our sense of the array implemented with in the stack implemented with resizable arrays. Any individual execution of push and pop can be very expensive if we have to copy the elements to the new array at precisely that time. But the observation is, because we always double the array right away, we create enough empty space so that one expensive operation pays for a lot of the future operations to be cheap. So that if you average them out, each is cheap on average. That's what amortization means. And in our case, we have there's a widely used, there's different proof techniques and templates that you can use to prove amortized bounds. I will focus on the one that I find most versatile. It's maybe not the most intuitive one, but it's the one that that works for all the problems that we will encounter. So I want to introduce the general version here right away. And the idea is we define a potential function. And that's some magic definition that you have to come up with. So this is reminiscent a little bit about the loop invariant. You have a proof template that's fairly simple, but you have a creative step where you have to understand the problem to see what you have to fill in for this step. That was the loop invariance, and here it's the potential function. Okay. Let's look at what the proof template works like. It defines an amortized cost for an operation, which is the actual cost, and in this case, -2 times the change in this potential. And this 2 is a constant that you usually work out after the fact. When you've done the analysis, you find that 2 is the right constant in this case, and so that's what you use. For other applications, it might be that you need a different constant. Okay, but that's a definition. Now let's look at what happens with push and pop. If we have a cheap operation, that means there is space in the array. The actual cost is just one array access. So by cost here, we count the number of array accesses. That is, again, a quick comment from the off. We used to talk in the previous unit, we talked about elementary operations, the dominating operations for a certain task. And here, for this simple application of a resizing array, how often do I access, read, or write a cell in the array? That's what we pick as an elementary operation. So our cost is the number of these array accesses. A cheap push and pop has exactly one of these array accesses. That's the actual cost. But the amortized cost has to add the change in potential. And here, if you look at this potential, now I should give you a little bit of an intuition. There's the bounds of 1/4 C and C, and n can be anywhere in this range. So n could be here. And n can move up and down via push and pops. So it can wiggle around here. And what this potential function does, the phi, is just the distance to the closest boundary. And in this case, we're getting closer to the lower bound. So in this case, phi is this distance. If n moves further up, it becomes this distance. Now, if you do a cheap push or pop, that means you move around with 1 inside this range. You're not at the boundary. So you go from here either to here or to here. If you go away from the boundary, you actually gain a credit. But we can't really use that because what we have to say here about the amortized cost has to be true in every case. If you move closer to the boundary, you lose 1 credit, by which I mean you lose 1 in phi. And because we double that, the amortized cost is 3 of such an operation. It's at most 3. It can be 1 if you really move away from the boundary. But that's the worst case. If you have one of these expensive operations, say a push, so that's the situation where your n reached the capacity and you have to double the array, then you have to copy the n elements from the previous array to the new. So that means n times you read and n times you write an array cell, plus the new element that you add in. So that's the 2n plus 1 array accesses for the expensive push. But it creates n credits in the potential function. Well, I would say that's actually n minus 1, right? If we're strict. So the amortized cost is 2. I think I just forgot that we also add 1 element at the same time. It might be the same here. If you add those 2 up, you multiply this by 2, and you add those 2 up, then you have the 2n cancels with that 2n, and then it's plus 1 minus 2. It's actually 3, is that right? Let's do the calculation in slow-mo to not screw it up. No, I was right. It's more expensive and it's 3 because I did double this. So that's the 2n cancels. And here we have the minus. All right. So it works out to 3. If you have the copying pop, that's similar, but now you reach the lower range of your capacity. Then again, you have to copy elements. And I think I screwed this one up badly. I think you also have 2n plus 1 copies because n is the current size. And but you only get half n credits. So this is the case where you notice that your constant here was not big enough. We have to change this to 4. Otherwise, this doesn't work out. We need that the factor here is big enough to cancel the actual cost. Now, if we add the 4 here, that will change the amortized cost of these operations, but it will only increase the constant. So this goes up to 5. And here again, we have the 4 plus 1, so that goes up to 5. And then similarly here, but let's do it in slow-mo again. Minus 4 times the 1/2 n minus 1. So those cancel, and then we have 1 plus 4. So this is also 5. Sorry for that confusion. I should have caught that mistake earlier. I'll fix the slides, but I think it was also insightful for you to see how these proofs are usually constructed. You start out with a constant here and see if it was big enough. And if not, you make it a little bigger. And usually either it works then, or you keep increasing the constant, which means your proof is flawed and something's wrong. Okay, let's I'll erase the side calculations. We have shown that in each of the cases, we have an amortized cost of 5. Now, what does that mean for a sequence of m operations? The total cost of that is at most this. So this is something I want to show. If we say AI is the amortized cost for the ith operation, so that's the actual cost plus the change in the potential. In our case, we say it's minus 4, and then the new potential minus the old potential. So by this phi I, I just mean the potential after step I. Now we want a bound on the total actual cost. But what we have is that our amortized cost is at most 5 for all the operations. So what we can say is if we sum up the amortized costs for m sequence for a sequence of m operations, that's at most 5m. But we also know that this sum is telescoping in the sense that if you insert the definition, you get the sum over all the CI's. And then we have minus 4 and then this sum where, well, let me write it down, but you can probably see this. In this sum, there's always one term that cancels the contribution from the previous one. So the only thing that remains from this is the total actual cost. And then we have minus 4. And what remains from this sum? What's not canceled is the last term, the phi m. And we have a minus phi 0 at the beginning, the initial the initial potential. And all the other terms in the middle cancel. And now we have a nice inequality where you can solve for the total cost of the total actual cost. And you just bring this to the other side. So the total actual cost is the sum of the amortized costs. That's 5m. And then we have to add the 4 phi m and subtract the 4 phi 0. But we can drop this is always just making it smaller, so we can, as an upper bound, do the 4 phi m. And so here, another little mistake, we get a bound, the total cost, that's the total cost, sum of the CI, is at most the total amortized cost, which is 5 times m, plus the final credits, that's phi m. Now let's see how we can fix that part. The total amortized cost was 5m. And okay, I switched between n and m. Let's keep it with n. Okay, let's m operations. So I should have written m here all the way. How big can the final credits be? The phi is always at most half n. So that part's correct, but we increased that constant to 4. And sorry, this was a lot of corrections. Plus 2n. Okay, that was a lot of work, but finally we've shown this bound, and that of course is theta of n plus m, which is the result we claimed here. So to wrap this up, if you have a resizing array and any number of operations m and a final size n, the total cost will be bounded in this way. The total cost is n plus m. And if you start with an empty array, the final size will never be bigger than m. So it's linear in the number of operations, which means each individual operation, on average, can only cost a constant time. That was amortized analysis of resizing arrays. That's probably a good point to check if you have any questions about this part. Again, I apologize for the confusion on the slides. Well, if questions arise later, we can address them then. If not, I'd like to conclude this part with queues, which are like the sister of stacks. They're like if you have to queue for getting into some shop, you can in-queue at the end, hopefully only there, if it's a fair queue, and dequeue at the front. So you add new people here, that's in-queue, and you dequeue at the front by taking the first person off and allowing them into the store. Implementation-wise, it's exactly the same as for stacks. You can use linked lists and you can use arrays. You have to be a little bit more careful because of the two ends, but it's not really a big difference. For a fixed size array, you have to deal with the wraparound in the queue, but you might have seen this before, and if not, it's not relevant for our class. And a final abstract data type that I want to mention is that of a bag. And it comes from the question, what do stacks and queues have in common? They're essentially special cases of just a collection. So this is also the Java name. It's roughly the same as a bag. A collection is just anything you can put items in and you can get items out. And I called this here delete any because you don't really have control over which item you get. You just remove any of the items in the bag. It's sometimes useful. It's not that you can implement a bag more efficiently than a stack or a queue. It's just sometimes useful to specify, I don't care about the order, use whatever is convenient for you. And yeah, that concludes the part of the very elementary basic data structures. Explicitly, I made this a bit longer than necessary because of the amortized analysis that we will reuse for different algorithms.